barely passed college algebra. I got a higher score in calc than I did in college algebra.
Has anyone taken Wolford? He doesn't want to teach each other, like, I hate my job. Anyways, let's get started.
It always feels like he's just like wants to show you how well he knows calculus and not actually teach it to us. I'm like,
All right, so let's take this one step further, and then we'll switch gears here. So we started with a full adder. We put them together to make an 8-bit adder. We added some extra stuff to make an adder subtractor with a function input. We can carry that even further and make a very general logic block called an arithmetic logic unit, an ALU. And there's a data sheet for one available on the website. And there's lots of different kinds of ALUs, but here's an example of one. It's got 20 pins, okay, ground and power, as usual. It's got A and B inputs, which should look familiar. It's got a C pin here, and it's got some other inputs like F, as in function. So here's what this does. It has 4 A inputs. That's your first number, A. 4 B inputs. That's your second number. It has 3 function select inputs, S0, S1, S2, that basically say what should this do with A and B. And it's not just an adder or a subtractor. It can do all kinds of things to A and B. And what you wanted to do is specified by these 3 inputs. And then there's 4 outputs, and they call them F because it's not just a sum. So function outputs 0 through 3. And there's some other pins we don't really need to worry about right now. And here's what this thing can do. So if all 3 inputs on your select lines are 0, the output is 0. It's a clear operation. If your inputs are 0, 1, 1, down here in this row, your output is the sum of A and B. If your inputs are 0, 1, 0, then the output is A minus B. Or you can get B minus A. Or you can do logic operations, AND, OR, XOR. Or you can drive the output to all ones, the preset condition. And all of that is bundled inside one chip. So if you're building, for example, a computer where you want to do different things, you want to add one to a variable, or you want to add 2 variables together, or compare them by subtracting and seeing if the result's negative, you can build it around a chip like this, an ALU, that'll do that sort of low-level grunt work and leave you to, process the outputs of that in whatever way you like. And so ALUs, so when I took digital logic, we had to design an ALU. I'm not going to do that to you, but I might show you my lab report that I did for that, because I found it recently and it was hysterical. My teacher was not happy. But here's a truth table for this thing, right? So it's got A and B inputs and selects, and they abbreviated this. There's actually 4 A's and 4 B's and a C, and then 4 F's. And here's what the output should be, right, for all of these. But it's a big truth table. Here's the circuit that implements it. Right, so this is what you'd have to build if you wanted to do this yourself.
Is that what you built?
No, I didn't build it. I designed it, and it wasn't this glorious. Yeah, so that's, and you could get this from writing out the truth table, doing the sum of products, and minimizing, and so on and so forth. But this is what's inside the chip for you. Right, this is why integrated circuits are so cool. Because for $1 you can buy this thing that does all of this, and the wires never get ripped out accidentally, and stuff like that. So, and this is a different version of it. All right, so that's called an ALU, arithmetic and logic unit. And it's usually part of a CPU, a central processing unit, like in a computer. And it's an example of a larger circuit. Right, this is definitely larger than our full adder. I fixed my resolution. So when we talk about integrated circuits, there's a kind of rough way that we can classify these things, which is small scale integration, medium scale integration, large scale integration, very large scale integration. Yeah. Oh, that's thank you. I was excited. I saw 5 hands up. I'm like, yes, questions. That's okay. All right, so small scale integration. And then medium, large, very large. And these are pretty obviously not precise terms, right? But typically small scale integration would be an AND chip, right? A 74 LSO8 with 4 AND gates. That's pretty small scale. It's a few transistors, okay? 10-ish transistors, something like that. A medium scale integration might be something like that ALU. Okay, it's got several dozen gates. It's probably got 100-ish transistors, maybe 200. Okay, so that would be medium scale. Large scale would be more on the order of thousands of transistors. And very large scale would be something on the order of, I don't know, maybe 50,000, 100,000 transistors. And today, right, you can find gates with on the order of 2 billion transistors. So this scale doesn't quite make sense anymore because there's so many large commercial parts that are just way off the chart here. But it's a nomenclature that was useful in the beginning of when people were using integrated circuits, but kind of approximate, not rigid rules about when does an MSI become an LSI. So we want to talk about some more of these sort of medium scale devices. ALUs are one example, but there's some other things we can talk about. But it's really hot in here, and it's our last class of the week, and it's dark and comfortable. So I'm going to switch gears here, and I'm going to give you some background for a little bit that I want you to have seen. I'm not going to test you on it, okay? So this is kind of sit back and take this in and ask questions as they come up, but you're not going to have homework on this. You're not going to see exam questions on this. But you'll bump into it later if you do more stuff with electrical engineering or possibly computer science. But this was stuff that I didn't really get exposed to until pretty late in the game. And I think it's good to know and think about and have seen. So let's start by talking about switches. Switches and logic. So just forget about resistors, and I said there's only one way to wire a switch. Put all of that aside for now, okay? Let's just think kind of like wall switches, okay? So you're putting in lights in your house, and you've got a switch. And there's a light bulb connected to this, and this is connected to power. And if you close the switch, the light turns on. If you open the switch, the light turns off, okay? Now suppose I take 2 switches and I hook them up like this. So here's my light bulb and here's my battery. And basically if you connect both sides of the battery to both sides of the light bulb, it lights up, okay? And let me call these switches A and B. And let me think of switches one of 2 ways. If my switch is in this position, I'm going to call that a 0. If it's in this position, I'm going to call that a 1. So 1 is connected, 0 is disconnected. And my light, if it's off, I'm going to call that a 0. If it's on, I'm going to call that a 1. And we can make a truth table for this. And what does this truth table look like? What's the first row? How would I fill that in? If both switches are a 0, is the light on or off?
It's like a AND gate, 0.
That's a 0. If that's 0, but this is closed, there's still no current flow. If you flip that, there's no current flow. But if both of these are 1, if they're both closed, the light comes on. So yes, that's exactly an AND gate. All right, let's do a slightly different version. So here's our battery. Here's our light bulb. Here's switch A. Here's switch B. So if they're both open, there's no way for current to get to the light bulb. But what if I just close the B switch? Right? My battery can go up there, go through the B, through the light, come back, the light will be on. If I just close A, same thing, and if I close them both, certainly that'll go on. We've made an OR gauge. All right, so we can make basic logic gates just using these simple switches. But we can't use these to build a computer very easily. And the main problem is the output is the brightness of this light. I look at it, and if it's bright, I say that's a 1. If it's dark, I say it's a 0. The input is the physical position of this little piece of plastic on the wall. Well, we don't have plastic switches here, but you know, the little thing you flip for the wall, that's the input. And the input is a fundamentally different nature from the output. The output is light, the input is a mechanical switch position. So there's no way that I can easily take this and say, take this output and connect that to this input. So I can't cascade these logic blocks together and build things like a full adder or a combination lock circuit. I want to do that someday, though. I want to get a bunch of students to volunteer. We're going to build a computer using light switches in rooms. And when you see the light go on next door, you're going to flip the switch and so on. I'm going to do that someday. It'll be a great YouTube hit. But this is the idea of a logic gate, right? If we had that way to take these outputs and use them to connect to other inputs, we could build a whole computer out of just light switches and bulbs. Okay, so there's a different kind of switch. I usually bring one of these in and I forgot. So here's our switch. So what's a switch? It can be as simple as a piece of metal that you push down and it makes contact. And when you release it, there's like a spring that pulls it back up. Right? So push it and it makes contact. Let go, it springs up, it breaks contact. Okay, how many people know what an electromagnet is? Take a battery, take a piece of wire, wrap it around a pencil about 100 times, connect the two ends to a battery, it becomes a magnet. Okay? It's a physics principle. And it's electromagnet. If you disconnect it from the battery, the magnet disappears. And it's just a piece of wire wrapped around a pencil. So if I were to take an electromagnet and put it right here, and I make sure that this piece of metal is something that will be attracted to a magnet, if I run voltage through here, this becomes a magnet, it pulls this piece of metal down, makes contact. If I disconnect the voltage here, it's no longer a magnet, the spring pulls this up, it breaks contact. I have a switch that I can control by adjusting a voltage. That's all I need to build a feasible computer. Because now I can take the output and instead of lighting a light bulb, I can use that to drive this controllable switch on another gate. So I can put these gates together. So So anybody know what this kind of thing is called?
Relay?
That's a relay. Do you work on cars?
Yeah, I
Okay.
actually have a certificate on it.
Cool. So at least with older cars, when you turn on the windshield wiper, or when you turn on the headlights, or when you first turn the ignition switch, you can sometimes hear a little clicking sound under the dashboard. That's a relay, right? Because to turn on your headlights to actually make them light, you need a lot of current, okay, coming from the car battery. But when you turn that switch, right, that's not connecting the battery to the light bulbs. That's running a little bit of voltage through a relay. And on the other side of the firewall, a lot of current is running through from the battery to the headlights. But that click you hear is just a relay. It's this thing coming down and making contact. All right, so relays are commercially available. And relays have been used to build computers. So a lot of early computers, 60s era, were built out of relays. And there's a downside to using relays. Well, there's a few downsides. One of them is that they're large. They're typically, that size. You can get really small ones if you want, but back 50 years ago, right, relays tended to be kind of that big. And if that's the size of one of your transistors, you're not going to build a billion transistor circuit, right? But even a modest sized computer would fill a room this size. Right? The other problem is that these are mechanical devices. You have moving parts. You have a spring-loaded piece of metal that comes down and makes contact, and then it flips up and it breaks contact. And moving parts are not good to have with computers. And I'll show you another problem. So this is a moth, and it's taped inside somebody's lab book. And this was a famous woman. Her name's Admiral Grace Hopper. She was an early genius in the computer field. She was also an admiral in the Navy. And she was working on a computer. She was working on some trig algorithms, and the code wasn't working right. And she did some debugging and figured out where she thought the problem was. She went back into the computer, right? This is when you could walk around inside a computer like Tron, right? Because it was this big room thing. And she found a relay, and there was a moth stuck inside the relay. And when the contact was trying to come down and make contact, the moth's body was in the way and it wasn't connecting. And it was a malfunctioning switch, basically. And so she pulled it out of there and she put it in her lab book, and she noted it first actual case of a bug, and she took that out and it worked fine, right? So these are mechanical devices. They're slow. You have to wait for this thing to physically move down here, and when you release it, it has to physically come back through the spring action and so on.
Couldn't the EMI be an issue too, if the shielding on those are bad or something?
That could be, although these might actually do better with like an EMP, right? But yeah, they're noisy, right? And they take a lot of power, because to make this electromagnet work, you need a lot of current. And there's crosstalk, there's interference. So if you put these things too close together, they're going to interfere with one another. So you can build computers out of these, but they're not ideal. The predecessor to this was in some case even worse, because it was built on vacuum tubes. So things like these. There's a good picture of some vacuum tubes. And vacuum tubes are another example of a switch that can be controlled electrically. But there's no moving parts inside other than electrons. You basically have electrons being shot out from something called an emitter, going to something else called a collector, and whether or not they complete that journey is controlled by something called a gate. And that gate can be electrically controlled to either allow electrons to flow or cut them off. So vacuum tubes were used in the earliest computers, and they're faster than relays. They may be a little more reliable in some ways, but they're made out of glass, They depend on a vacuum inside, and the vacuum seal eventually fails. And they take a lot of power. So when they're operating, they're usually glowing red inside because you're heating up a piece of metal inside to cause it to emit electrons. So they're faster, but they're very error prone and very expensive to build and very large. So what's a transistor? A transistor is a solution to these problems. And here's a picture of a typical transistor. So there's a schematic diagram of it. And this is called the gate. And usually this is called the drain. And this is the source. Doesn't matter which is which. And basically, this is like a voltage-controlled resistor. Depending on the voltage we put on the gate, this either looks like a wire or it looks like an open circuit. So with this kind of device, if we put 5 volts on here, say, this may connect the drain and the source together, as if it's just a wire. If we take off that voltage, it will look like an open circuit, right? Basically the same thing we're doing with a relay. If we put voltage here, these points are connected. If we disconnect the voltage, these are disconnected. So it's kind of like that version of a relay. And this is what computers are built out of. So how can we do this? Well, we've already seen something we can do with switches that either make contact or break contact. Right? We know how to use those to generate a 1 or a 0, don't we? That's what you've done in your labs so far. So what do? We take 5 volts, we put in a 1K resistor, but instead of a mechanical switch, we throw in a transistor. And here's our output. And now if we put 5 volts on here, this gets connected to ground, our output is a 0. If we put 0 volts on here, this is disconnected from ground, our output goes to 5 volts, this is a 1, this is an inverter.
Is it using magnetic energy as well, or what kind of or?
That's a good question. So I'm going to punt on that and just say at some level electricity and magnetism are really the same thing. So it doesn't use magnetism in the way that a relay does, but the whole way that electrons flow and that semiconductors, which is what a transistor is made of, the whole way they work kind of includes magnetic aspects as well, but no, it's primarily electrical. But electricity and magnetism are duals in most ways. If you repeat any of this to a physicist or somebody who does engineering for a living, they'll laugh at you, because this is a really, really simplified version of what's going on, but this is the version that I use when I want to work with transistors. Okay, it's definitely a whole lot more complicated, which is why it took so long to come up with transistors in the first place. But this is functionally what's going on. We're either making connection between the two ends or we're breaking it. So we can make inverters, and we can mimic what we did in the beginning of this. So if either of these is a 0, the path from the output to ground is broken. Right? If B is a 0, for example, even if A is connected, we can only get down to here and there's no path to ground. So if either of these is a 0, there's no path to ground, the output's going to go through the resistor to 5 volts, we're going to get a 1. But if both of these are 1, this is closed, the output comes down to ground, the output is a 0. So what kind of gate is that?
Or
It's a NAND.
How'd you guess them all?
It's in there eventually, right? So I had to do this before I knew the answer. So just invert it, and that's an AND. So this is a NAND gate. What do we know about NAND gates? What's cool about NAND gates or NOR gates? Apollo. You can use them for everything. If you can build one of these, you can build any kind of gate you want. So this is enough to build adders, ALUs, CPUs, whatever you want. But we can also directly build an OR gate or a NOR gate, right? We can do something like this. And if you work through the logic, if either A or B is a 1, this will come down to ground and your output will be 0. If they're both 0, then your output will be high. That's a NOR gate. So we can build, and since we can build a NAND gate and we can build an inverter, we could take this and put it into an inverter and we'd have an AND gate. And the thing coming out is just a voltage, and that's the same as the thing coming in. So they cascade, they go together nicely. So we can build computers out of transistors, which is a good thing, because that's what we do. Now, there's different kinds of transistors, and they're all nominally called semiconductors. So have you heard that term? Okay. And usually they're made out of some kind of sandwich. And there's usually two types of material. We call them N-type and P-type. And if we have two N's with a P in the middle, we get one type of transistor. If we have two P's with an N in the middle, it's a different type. But basically, this is your source and drain, and this is your gate. And this is an even worse explanation of what's going on. But the way this is set up, this is not a conductor. Okay, it's not something like metal that lets electrons flow. So if you put current here, it has no way to get to the other side of this sandwich. But by applying an electric field here, we change the nature of this and kind of turn it into a piece of N material. And that allows the stuff to flow through. Horrible explanation for what's really going on. But that's, in a nutshell, what's happening. We put a voltage on that gate layer, and it changes its characteristics so that it changes from being non-conducting to conducting. And it lets things flow through. You can do a whole physics course on semiconductor theory and get into the details of what's actually happening. But that's enough of an understanding to be able to work with these things. So there's an observation we can make. Actually, somebody made it last week, which is that if we put a 0 in here so that this is disconnected, our output's at 5 volts, but we have a resistor here, and we have current flowing through here, and current through a resistor gives us power, and so this is generating heat, right? And this is inefficient. So there's two types of transistors. So these are called MOSFETs. So Metal-Oxide-Semiconductor field effect transistor. Okay, and there's two types of MOSFETs. There's nMOS and there's pMOS, depending on how this NPN stack is laid out. And one of these does what I'm describing. If you put voltage on here, the source and drain are connected. If you put 0 volts here, they're disconnected. The other one does the exact opposite. If you apply a voltage here, these become disconnected. If you take away the voltage, they connect. And we can use those two types of transistors together, and we can create a circuit like this. see if I can get this right the first time. And I may have my symbols backwards anyway, but I'm going to be consistent with you. So this little circle here is saying that this has the opposite behavior. If you put an input of low voltage, this will be connected. High voltage, it'll be disconnected. Okay, no resistors in sight, right? So what does this do? If your input is 0, this is disconnected, this is shorted. Your output goes directly to 5 volts. Very, very low resistance. So you don't have that residual power draw, but we still get an output of 1. If your input is 1, this gets shorted, this gets disconnected, your output goes directly to ground, you get your 0 out. So this is an inverter also, but without that annoying resistor going up to 5 volts, wasting power. And we have two types of transistors, an NFET and a PFET, and they're working in complements to each other. Basically, one of them is either pulling you up to 5 volts and the other is out of the picture, or one of them is pulling you down to 0 and the first one's out of the picture. So this is called complementary metal-oxide-semiconductor, cMOS. And that's the technology that's used most places today, in your phone and your laptop and so on. And we use cMOS instead of these ones that have resistors, because these are much lower power, significantly lower power. Enough that we can have 1 billion, 2 billion transistors and drive it for 6 hours off a battery.
Is that similar to like the cMOS battery on an older motherboard?
So,
Or UEFI?
yeah, so that battery is supplying power to a cMOS circuit, right, which is being used to hold maybe the real-time clock or something like that. You don't want to power a very big circuit like this with a battery because it's constantly pulling energy, right, and it's just not going to last very long. But with the advent of cMOS circuits, they're so low power that you can get a small, 2032 watch battery, and you can drive this for a few years maybe, if there's not a lot of transistors. So yeah, that would be a backup on a motherboard. And if the battery died, then bad things happen. All right, there's other kinds of transistors out there. There's other kinds of logic gates. So early computers used this, and this was called nMOS. And I've made one nMOS chip in my life. Very easy to work with, but fairly power hungry. This is there's a pMOS also, which uses the opposite kind of transistors, but for technical reasons it's harder to manufacture. So most things were nMOS. But then cMOS, conducive to larger numbers of transistors because of the lower power. But there's other things. There's TTL. So transistor logic. And this was a popular family in the 70s when integrated circuits first sort of came generally available. Texas Instruments started making TTL chips, and you could buy these big orange data books that were just filled with the data sheets for all their devices. And that kind of really standardized everything. TI sold a 7404, which was a 6-pack inverter. Right? Today we get 74LS04. It's not TTL, it's a different technology, but it still uses the same pinouts and so on and so forth. There's ECL, which is emitter coupled logic, totally different approach, different way to wire up your transistors. ECL was cool because it was really fast, right? All of these things have a certain delay. When you put a voltage on here, you're basically kind of filling a region with electrons, but that takes time. Not a lot of time, nanosecond maybe, 1/1000th of a second, but it's not negligible. ECL was really fast, but it took a lot of power. your circuits would get unbelievably hot. So how many have heard of Cray computers? Oh, sadness. Seymour Cray was one of these like geniuses ahead of his time. And he made these beautiful machines like this, where they'd have like, you know, a seating area outside them. Just amazing stuff. And a lot of these, they had kind of this glow to them because they were using Freon to cool the circuits because they were ECL based and they would get so hot, right? Think overclocking, right? But actually running it in a way that it's designed to run, but that gets extremely hot. So they had to be cooled usually with some kind of liquid coolant. But Cray computers for a while were the fastest computers on the planet, right? Fastest artificial computers. And they were export controlled and all kinds of good stuff. And that was based on just different technology and really, really clever architectures, right? Because there's a million ways you can build an adder, and some are slow and easy, some are fast and difficult. So Cray did everything the fast, difficult way. All right, so that's kind of a crash course on sort of what's at the root of a lot of this stuff, the transistor theory. Like I say, you're not responsible for that, but I want you to have seen it. And knowing something about it will help down the road with other things. Just kind of going back to it in your head. Plus, if you're double E, right, you'll dig into all this stuff in detail. You'll build the stuff at the transistor level. So you'll definitely see it again there. So I'm going to let you out a few minutes early, but let me tell you what we're going to do on Tuesday. I want to talk about some more of these larger scale devices, including something called a programmable logic array. So imagine a piece of circuitry that instead of taking wires on a proto board and hooking them up the way that you've been doing, you could hook this thing up to your computer and somehow download information into it and have it wire itself. And now you would have a chip that contained whatever circuit you wanted. That's basically what a PLA is, or more generally, programmable logic. So we're going to talk about that on Tuesday, and that's also going to be part of your next lab. And we're going to come back to that at the end of the course and extend that into something called field programmable gate arrays, and you'll actually get to work with some of those. So we'll be doing good stuff next week. All right, have a good rest of your week. I will see you next time.